Hello all, welcome to this course on time series modeling and forecasting using R. Now we are sort of entering a new week and then slightly different idea, and then the idea is in front of all of you. So we are going to analyze or try to find out as to what one means by multivariate time series, right, or multivariate time series analysis. So far whatever we have covered would be simply univariate, isn't it? I mean, we would be analyzing, let's say, a single data. So be it stock price or temperature data, rainfall data, whatever. But then you have YT and then its iterations, or something like YT, then YT plus 1, YT plus 2, etc. But then the whole idea is that whatever models we've studied so far, so AR, MA, ARMA, ARIMA, even ARFIMA, all those models were applied on a single series. So whenever you want to analyze or let's say model and forecast a single series, that idea is called as univariate time series analysis. And if we slowly transition into multiple series, then that idea is called as, let's say, either bivariate or trivariate, or in general multivariate time series analysis, right? So in this week we'll spend some time on understanding the idea of multivariate time series analysis. Why is it important? What all aspects we have to take care of when we want to analyze multivariate time series analysis, right? What are the interrelationships between, let's say, any two series, and so on and so forth, right? And of course down the line we'll have a half an hour session which would be practical in R, all right? Okay, so firstly, motivation. So why should we study, or why should there at all be an idea of sort of understanding or analyzing multivariate processes? Okay, so a couple of points here. So multivariate processes, which are also called as vector processes. So you have two names, so either multivariate series or vector series, emerge when several related time series processes are observed simultaneously over time. Okay. So maybe I'll pause here for a second just to give you a very quick idea or example. Of course, you'll see similar examples later on also, but just to start the motivation idea. So let's say you have YT and at the same time you have XT, right? And you assume that there should be some relationship between XT and YT, but then XT and YT are completely different series, right? In what terms? So you have YT, then YT plus 1, YT plus 2, etc. in the future. Similarly, you could have, let's say, XT, then XT plus 1, XT plus 2, etc. in the future, right? Now, how do you analyze and how do you understand the interrelationship between two series? So let's say XT and YT, right? This is the idea of kind of putting forward the multivariate processes idea, right? So in short, or in other words, how do you model these two series simultaneously, or let's say together, okay, is the whole idea, right? And then second point in the motivation slide is that one might be interested in investigating the cross relationships between the series. So for example, how is, let's say, XT plus 1 related to, let's say, YT plus 2, or how, let's say, YT plus 1 might be related to, let's say, XT plus 2, or YT plus 1 might be related to simply XT plus 1, and so on. So all these are cross relationships among the lags also, right? So if such a thing exists, it will be very suitable to study them together or put forward a model together, or which is sort of combined on both XT and YT. Okay. So this is exactly where the idea of multivariate time series analysis or multivariate time series processes emerge, all right. Now the objectives. The objectives for jointly analyzing and modeling the series are as follows. So you have two objectives here, and of course there might be many more, but then just the important ones we've sort of listed down. So the first one is to understand the dynamic relationships of the series over time. Now again, couple of points to note here is that dynamic relationship. So dynamic relationship means how the relationships evolve over time, right, of both the series over time. So let's say YT plus 1, YT plus 2, YT plus 3, at the same time XT plus 1, XT plus 2, XT plus 3, etc. Right? So these sort of relationship is called as dynamic relationships of the series over time. And second point is to improve accuracy of forecasts for individual series by utilizing the extra information or the additional information available from the related series. Right? Now again, the second point is also important, that let's say your goal is to forecast YT down the line, right? So YT is the series in focus, and then your goal is to forecast YT. Let's say yt plus 10 or yt plus 11, yt plus 12, whatever. Of course, depending on all the historical time points, right, up to let's say yt plus 9, but let's say the focus is to forecast yt. And then you have another similar series, let's say xt. So, how can you sort of make use of xt and its values to forecast this yt, right? So, such sort of cross relationships when it comes to in between the lags or even for the forecast of individual series, then we have to study some multivariate time series processes, all right. Okay, so we will put forward some examples right away. So, the first example could be in finance. So, let us say price movements in one market can spread easily and instantly to another market. So, let us say you have two markets, both of them are separate, and then whatever movements you are observing the first market, those could be spread or those could impact the movements in the other market, right. For this reason, financial markets are highly dependent on each other. So, I will give you a very simple example. Let us say these days people trade in cryptocurrency. So, again I am not saying that one should trade in cryptocurrency. There is a small disclaimer that I am not for or for that matter against trading in cryptocurrency, but just a small example that the trading activity in general has risen, right. And if you are, let us say, trading in two cryptocurrencies, so Bitcoin and Ethereum, and one can actually assume that there exists some correlation between Bitcoin and Ethereum. So, whenever the Bitcoin price rises, the Ethereum price also rises and vice versa. Okay. So, one of the assets there, which is let us say Bitcoin, and its price is affecting the price of the other, which is Ethereum, right. And in that case, both these financial assets or financial markets in other terms are highly dependent on each other. Okay. So, we have to consider them jointly to better understand the dynamic structure of the global market. So, now if you assume that these two are the only currencies that one can trade, of course, I mean this is a hypothetical situation. So, let us say you only have two currencies, so Bitcoin and Ethereum, and then Bitcoin and Ethereum prices are sort of, they have some dependency between them. So, why not put forward a model which comprises of both Bitcoin and Ethereum? So, why not put forward a bivariate model structure on both the Bitcoin prices and the Ethereum prices? And why exactly? To better understand the dynamic structure of the overall market. So, overall market consists of these two, right. So, if you put forward a bivariate model rather than modeling them individually, you can actually know the intricacies and dependencies between the two assets which are there. Okay. So, knowing how markets are interrelated is of great importance in finance, of course, right. And one more second point is that if you have an investor, so for an investor of a financial institution holding multiple assets plays an important role in decision making, right. So, these are some use cases or some examples where one might go for an extension like let us say bivariate modeling or multivariate modeling and so on, right. Now, a second example would come from economics. So, let us say one may be interested in simultaneous behavior of interest rates or inflation, money supply, unemployment rates, etc., right. So, focus may be on simultaneous study of time series of let us say GDP, percentage of people below the poverty line, unemployment rates, female headed households, crime rates, average income, minimum wages, etc. So, all these are economical examples, and then one might be interested in studying the interrelationships between any of these two. So, let us say for example unemployment rate and then average income. So, if you want to put forward a bivariate model comprising of both unemployment rate and average income, so for that we require some multivariate time series analysis tools. Okay. So, hopefully I have motivated all of you enough that why should you transition from analyzing series individually, which is nothing but univariate, to something like bivariate or trivariate or in general multivariate, alright. Okay, so a couple of last examples. The first one comes from environmental sciences and agriculture. So, let us say joint study of time series observations of maximum and minimum temperatures or rainfall or in general some atmospheric humidity, wind speed, direction, etc., and let us say the total production of wheat. So, here you have two series. So, the first one could be let us say maximum and minimum temperatures or rainfall or humidity or wind speed and direction, and the second series could come from agriculture. So, let us say total production of wheat. Now, of course, one can expect that the total production of wheat that particular month or that particular year sort of also depends heavily upon the other environmental aspects. So, rainfall, temperature, humidity, wind speed, direction, etc. Isn't it? So one may assume that production of wheat, which happens, has to be highly correlated with some other environmental aspects also. So putting forward a bivariate time series model comprising of both one of these aspects above and let's say production of wheat makes even more sense. Okay. And one small example from let's say health and environment related studies, something like this. So joint study of air pollution level or number of asthma patients visiting the hospitals and let's say number of registered cars in a city, etc. So one can actually find out a lot of interconnections between two variables to sort of put forward a combined model which is a multivariate time series model. Okay. Okay, so now we'll quickly go over some practical examples. So here you see some European stock markets or European stock indices, and then between 1991 and 1998, right? And then here you see a small index. So each and every color sort of points to a different index. For example, FTSE is the UK index, right? Then DAX is the German index. Then SMI is the Swiss index, and then CAC is the French index. Right. So France, Germany, UK, and then Swiss. But then here the whole point is even if you are plotting them on a single plot, but then can you somehow find out some interrelationships between any two series or let's say any three indices or for that matter all of these indices, right? And hence we can actually go ahead and then try putting forward a multivariate time series structure to capture the dependencies between all these indices. All right. One more example. So let's say you have two series. The first one is Nottingham average monthly temperatures, and then we have heating demand. So the red curve gives you the heating demand, and then the blue curve gives you the temperature data. So is there any relationship between the temperature data and the heating demand? Now, of course, ideally they should be, right? So why not study them together, right? So whenever you have more heating demand, or whenever you have less heating demand, what is the effect on the temperature or rather vice versa. So when the temperature is more, what about the corresponding heating demand, or when the temperature is less, what about the corresponding heating demand, and so on, right? And probably one last example is let's say US economic time series. So here you have three series. So population, unemployment rate, and savings rate. So this middle one, which is given in green, is called as personal savings rate. Right. So is there any relationship between the population, the saving rate, and the unemployment rate? Right. This again can be put forward in a trivariate kind of a modeling scenario, and then we can understand them better. All right. So again, the idea is that these are some practical examples to tell you that under what situations probably analyzing them separately might not be feasible or might not be useful. So as to one should go with some let's say bivariate modeling or trivariate modeling or multivariate modeling. All right. Okay, so these could be some potentially interesting questions that one can ask, right? I mean, based on some of the earlier graphs and then in general some of the interdependencies between multiple series is, then these are some potentially interesting questions that one can ask. So firstly, let's say, do some indices have a tendency to lead others? I mean, so what do you mean by that? So let's say if you have two series, then does one of the series sort of leads the others? So information which is passing in the first series is sort of ahead of the information which is there in the second series. So does the first series affects the second series in a positive way or sort of in a directional manner, right? So such questions could be answered. So the second one could be, are there feedbacks between the indices, right? Does the information in the first series has anything to do with the movement in the second series and vice versa, right? Third question could be something like, how do impulses mean shocks, etc., transfer from one index to the other? So again, if you go back to the European indices example that we saw earlier, so let's say you want to find out if the FTSE index has anything to do with the DAX index, or is there any relationship between FTSE and DAX indices, or rather if you see any shock in the UK market, so does that or will that have any impact in the German market, right? So these are some questions that one can try to answer. Last one could be, how about common factors such as disturbances, yields, trends, risks, etc. So is there any common disturbance factor or any common shock which is there in both the UK market as well as the German market, right? And so on and so forth, right? So such questions could be easily answered through an empirical investigation using tools developed in a multivariate framework. Make sense? Okay. So one very small disclaimer that before we sort of enter this week, so there will be a lot of theory which would be coming in, right? And why exactly? Because one can imagine that if you want a univariate distribution, things are slightly easier. The moment you transition into bivariate, let's say bivariate normal, bivariate exponential, whichever distribution you take, there would be something which would be slightly advanced, right? So I'll try to give you some refreshers. For example, the refresher that you see in front of you is a small refresher on matrix algebra. So we'll be using some matrix algebra here, right? And then again, don't worry. So don't be afraid. So I'll try to explain each and every point wherever, let's say, some hi-fi matrix comes in or some advanced techniques come in, right? Then I'll try to explain them in a bit more detail, right? So small refresher about matrix algebra, and then we'll see from the next session onwards as to how do you put forward all these ideas and then try to model using a multivariate framework, all right? Now again, I'll probably suggest that if you don't like matrix algebra or if you don't know matrix algebra much, then pick up any basic textbook or even, let's say, Google the basic ideas about, let's say, some basic matrices. I mean, what do you mean by inverse? What do you mean by determinant? Let's say, or let's say, what do you mean by trace of a matrix? Or how do you find out the inverse? Or what do you mean by a symmetric matrix, right? Skew symmetric matrix. So very basic knowledge about, let's say, some matrices would be slightly beneficial to understand this particular week. All right. For example, eigenvalues and eigenvectors. So where exactly can we make use of eigenvalues and eigenvectors of a matrix when we sort of study the multivariate time series processes framework? Okay. But just a very quick refresher about eigenvalues and eigenvectors. So let's say you have A, which is a matrix. So A is a matrix which is n cross n. So A is a square matrix of order n cross n, and then we focus on this polynomial. So f of lambda equals determinant of a minus lambda into in. Now firstly, what is in? So in is nothing but the identity matrix, right, of order n. So identity matrix of order n. Now again, identity matrix, if you're again not very comfortable, go back and try to study. So identity matrix is nothing but a matrix containing ones on the entire diagonal and zeros on the off diagonal, right? And the order of in is nothing but n cross n also. So for example, this would be a 2 cross 2 identity matrix, right? Or this would be a 3 cross 3 identity matrix, etc., right? So in general, in is nothing but an n cross n identity matrix, and using that identity matrix and A, we are creating this polynomial. So f of lambda is determinant of a minus lambda into in, is a polynomial of order n in lambda, of course, right? And lambda 1, lambda 2, lambda 3 up to lambda n are the n roots of this equation, is it? So if you form this equation, so determinant a minus lambda in equals 0, then naturally lambda 1, lambda 2 up to lambda n would be nothing but the n roots of that equation, and hence a minus lambda in is a singular matrix because this determinant is 0, right? So a minus lambda in is a singular matrix, and thus there exists a vector, let's say qi, such that this should hold true, right? Now again, I am not saying that you should go back and try looking at the proofs, right? I mean, one can actually prove all these things, but the proof is not the matter of fact here, or proofs are not really important here. I mean, of course, if you are more interested, then go back and then see as to why should there be such a vector qi and all these things, right? I mean, this sort of depends on how much time you can spend outside the class and then try to refresh, let's say, some very basic matrix algebra, right? But again, coming back to, just to summarize this, that a minus lambda in should be a singular matrix, and thus there should exist a vector qi such that this equation should hold true, right? And going from this step to this step is not difficult. So one can actually open the brackets, multiply by qi, and then take one of the items on the right side. So a into qi equals lambda I into qi. So this is a famous equation which comprises of eigenvalues as well as eigenvectors, right. So, lambda I going from 1 to n are the n eigenvalues of the matrix, and then Qi, I going from 1 to n are the eigenvectors of the matrix A. Okay. So, these are Qi's are the eigenvectors, and then lambda i's are nothing but the n eigenvalues of this matrix A. Okay. So, hopefully, the idea of eigenvalues and eigenvectors would be slightly easy to understand now that I have sort of given you a refresher on these ideas, hopefully. Okay. Okay. So, going forward, so again let A be the same, let us say n cross n square matrix, and let us say Q1, Q2, Q3 up to Qn be the n linearly independent eigenvalues corresponding to eigenvectors lambda 1 up to lambda n. Now, here one small mistake is there, that Q1, Q2, Qn are n linearly independent eigenvectors. So, this should be eigenvectors here, right, because Qi's are the eigenvectors, isn't it. So, Qi's are the eigenvectors corresponding to eigenvalues. So, these lambdas are the eigenvalues. So, corresponding to each eigenvalue lambda 1, lambda 2 up to lambda n, right, we are putting forward some linearly independent corresponding eigenvectors, which are Q1, Q2 up to Qn, right. Now, let us denote this collection of all the eigenvectors as capital Q. So, capital Q denotes the collection of all these eigenvectors. Then what happens is that if you pre-multiply this Q with the matrix A, so AQ, then what would happen? So, for this you have to go back a slide, which is right here, and then how do you make use of this expression? Because you know that AQi equals lambda iqi for every I, right. A into the eigenvector should be equal to the eigenvalue into the corresponding eigenvector. So, A into Qi should equal to lambda I into Qi for all I, of course. So, this should be true for all I. Hence, can't you write down something like this? So, the matrix AQ would be nothing but equal to the eigenvalues lambda 1, lambda 2 up to lambda n into the corresponding eigenvector. So, Q1, Q2, Qn, right. So, AQ would be nothing but this collection, right. So, again just to summarize, so we started with this capital Q containing all the eigenvectors, and then A into that collection AQ would be nothing but the corresponding eigenvalues into the eigenvector. So, lambda 1 Q1, lambda 2 Q2 up to lambda n Qn, and for this we are giving a different notation. So, Q is still there because you still have the eigenvectors here, and then this is nothing but capital lambda. So, this notation is again a Greek notation which denotes lambda again. So, AQ should be equal to Q into this lambda, where lambda is nothing but a diagonal matrix containing all the eigenvalues in the diagonal, right, and then off diagonals are zeros. Make sense? So, this lambda structure is what, like what? So, this lambda matrix is nothing but lambda 1, lambda 2 up to lambda n, and then zeros everywhere else. Okay. So, this is a diagonal matrix containing the eigenvalues in the diagonal and all other values are zeros. Okay. And then using this equation or this expression that you see here, what would happen if you pre-multiply by Q inverse? So, Q inverse AQ would be nothing but Q inverse Q lambda, isn't it? If you pre-multiply by Q inverse on both sides, so Q inverse AQ equals Q inverse Q lambda, and of course, Q inverse Q would be identity. So, you are left with lambda. Okay. So, this is a famous equation. So, Q inverse AQ equals lambda, where Q consists of all the eigenvectors, A is the underlying matrix, and lambda contains all the eigenvalues. All right. And these are some of the properties that one can actually talk about. So, for example, determinant of A is nothing but product of all the eigenvalues. Trace of A is nothing but summation of all the eigenvalues, right. And if you have something like this, so A to the power m, then this equation should hold true, that A to the power m is nothing but Q into lambda to the power m into Q inverse, right. So, all these are some elementary ideas in matrix algebra. So, if you pick a very basic book on matrix algebra, or again let us say some elementary course notes on some linear algebra or matrix algebra, then all these things would be there. right? So far we studied eigenvalues, eigenvectors, and then relationship between, let's say, eigenvalues and eigenvectors. And then going a step ahead, what do you mean by, let's say, this capital Q, or what would happen if you multiply capital Q by A, right? So that is nothing but Q into lambda, where lambda is a diagonal matrix containing all the eigenvalues, and hence eventually we can focus on such an equation. So Q inverse AQ is equal to lambda, right? And these are some properties that one can actually prove, that determinant equals product of all the eigenvalues, trace of the matrix equals summation of all the eigenvalues, and so on, right? Okay, so now what we'll do is we'll transition into the idea of a random vector, and then we'll discuss some properties of a random vector. Okay, so firstly you should understand what you mean by a random vector. So let X be a p cross 1 random vector. Okay, so random vector means nothing but something like this. So let's say you have x1, x2 up to x, let's say p, right? So x1, x2 up to xp. So this would be a random vector. So random vector means a vector containing several random variables. So each one of these items are nothing but random variables, isn't it? So x1, x2 up to xp. Okay, so let X be a p cross 1 random vector, and these are some properties of the random vector that one can actually follow, or one actually has. So expectation of xi. So if you take the expected value of any of the elements of the random vector, which is nothing but equal to mu I for all I. So this is given by, or this denotes the mean of the corresponding xi, right? Or further, if you have something like expectation of xi minus the corresponding mean whole square, right? So expectation of xi minus mu I whole square, this gives you the variance. So sigma ii. Or if you have something like expectation of xi minus mu I into xj minus mu j, this is denoted by sigma ij, which is nothing but the covariance between xi and xj. Now from here going forward, one should understand that the idea of a random vector would be very important, because, and why exactly? Because you are trying to analyze multivariate time series processes, so which are more than one, isn't it? So like we took the example earlier also. So on one hand you could have yt and xt, right? So how do you sort of combine these two individual time series processes in a vector, which is nothing but a random vector, right? Because each one of these, so xt and yt are random variables in themselves. So if you combine them in a vector form, it's called as a random vector. And then on top of that, I can talk about expectation of individuals. So E of yt or E of xt, or variance of yt, variance of xt, right? And one last thing we can talk about here is the covariance between xt and yt. So all such things could be studied when we have some idea about a random vector. Okay, thank you.